and my presentation will be about a slightly different topic, as you can see on this slide. It is called Analysis of Ecological Building Envelopes using Grasshopper, and it will address the question how we can use computational design tools, workflows to promote biodiversity in the urban environment. But before I start, I would like to give you an overview about our company, McNeel, and our products. My name is Verena Vogler. I'm part of the McNeel team for nearly 10 years now. Back then, I started as a part-time Rhino trainer and German tech support at McNeel Europe while working at the university as a researcher. I used in my research Rhino and Grasshopper to design and fabricate artificial coral reefs, which was really interesting to work at the company, but also to work in research at the same time. And today I'm the responsible person for R&D activities and our programming course program that is designed for Rhino users with a strong interest in development. So we offer courses for Grasshopper, Python, and C# at different levels. So maybe you have seen it around. And if you want to learn more about it, you can just come up to me and ask me some questions. So who are we? The McNeel story in a nutshell. Robert McNeel Associates was founded in 1980, and it is a privately held, employee-owned company with headquarters in Seattle and regional offices worldwide. Compared to other software vendors, we are a small company with 130 employees divided into development and into support. We have more than 500,000 users worldwide, 10,000 of them are schools, and furthermore, we work with more than 500 resellers, authorized Rhino training centers, and third-party developers. We strongly support Rhino as an open development platform. So our SDK is public to access our geometry kernel, and the 3D file format is also open source and freely available for over 20 years now. Our core value is to deliver a product that truly passionates our customers, to naturally promote this product by an authentic type of recommendation. So one user recommends it to another user. And our company also actively commits to empowering developers and to foster a strong sense of the community, which are our users. So our main products, you might know them. They're Rhino and Grasshopper. Rhino is a powerful freeform surface modeler for Windows and for Mac. And Rhino supports the creation and editing of NURBS curves and NURBS surface geometry, mesh geometry, sub-Ds, and point clouds. So as such, it is industry neutral. But as we are in a digital and additive manufacturing symposium, Rhino is used in different industry, and into today, manufacturing is a powerful application of Rhino. It supports a variety of file formats that are compatible with 3D printing, and hopefully we will have also soon the 3MF format. The example on this slide shows something that you have seen probably in the exhibition area. It's a footwear designed by René Meder that he realized together with Verena, the ADMS model by Verena, and it was created in Rhino using sub-Ds. With the release of Rhino 8 last October, we introduced the shrink wrap command, which creates a watertight mesh around open and closed meshes, NURBS geometry, sub-Ds, and also point clouds. So it's not only ideal for creating meshes for 3D printing, but also for reverse engineering. So we have seen how people use it for the conversion from 3D scan data to sub-Ds, to NURBS, and then to fabrication. So it's how René mentioned it, it's like turning garbage or rubbish to gold. That's how we sell the tool, like this command or this tool. So Grasshopper, how many of you know and have used Grasshopper? Wow. Okay, that's a lot. I didn't expect that many, actually. Okay, so, but I will tell you what it is. Grasshopper is a visual programming environment that's tightly integrated with Rhino's 3D modeling tools. It was introduced by David Rutten as explicit history back in 2007 with the aim to make Rhino parametric modeling tool. So Grasshopper allows you to have a map of the creation process of your design, which is the Grasshopper definition that you might be familiar with. And it also, and also to make changes in your model's history that then affects the final outcome without having to remodel. So you can see here, you can go back and change the size of the box. You can change the number of points inside of that box, and then this affects the Voronoi and then the edges. And then you can also create a sub-D fattened kind of structure from that. So this is the way Grasshopper works. And since back then, Grasshopper allows users to build custom computational workflows, algorithms, generative forms, parametric geometry, and data models. And David actually has spent a lot of time to make this user experience a joyful one for designers and engineers that do not have a background in programming. So after a brief introduction of our company and our products, I would like to present the work that we're doing at McNeel Europe R&D. McNeel R&D participates since 2016 in European research projects. They are funded by the European Commission. And during the past years, we have worked in 4 Horizon 2020 projects with the goal to test our new frameworks and open APIs in new fields such as geomatics, neuroscience, and also ecology. So our latest project is called ECOLOPES, and in the project, a team of ecologists, computational designers, architects, and experts for human-nature interactions, they jointly work together on a conceptual idea of ecological building envelopes, which we call ECOLOPES. And the ECOLOPES project aims to address the negative impacts of rapid urbanization on landscapes and ecosystems, which are biodiversity loss, invasive species spread, and reduced ecosystem services, which affect both negatively nature and also human well-being. So traditionally, architects have not focused on designing for biodiversity, and also urban planners, they often overlooked architecture as they concentrated on the spaces that are free of buildings, which are parks. So in this project, in ECOLOPES, biodiversity is a central driving force for architectural design, and we try to find a way to include, besides human needs, also those of other species, so such as microbiota in the soil, plant species, and animals. So we try to include them in the design process, their requirements. Well, as we are a software development company, our role in the project is rather technical. We are responsible for integrating an ecological model into a computational design workflow, and we try to offering it as a free tool for architects and designers, so it would be a free Grasshopper plugin. So first of all, what is an ecological model? An ecological model is a simplified mathematical way or program to represent a complex ecosystem. So you could imagine it as some sort of game of life, and the output, there are 2D maps that display, like you can see one of those here, that display biodiversity values over time at the scale of a region or of a country. And here the UCD Dublin, they developed a biodiversity map of Ireland. So this is mainly this that's the scale these models work in. So the questions we asked ourselves was, how can we adapt these type of models to work on a much smaller scale? How can we operate them in 3D? And how can we simulate an ecosystem on a building? So on the right-hand side here, you can see the validated ecological model, and this is developed by ecologists in the project from the Technical University of Munich, and it computes species dynamics between microbiota in the soil, plants and animals in 2D. And what we did is we substituted the 2D grid cells by a 3D voxel model and generated geometry-related inputs with new grasshopper functions. And these functions are related to soil distribution, soil type, soil depth, shading, and there are much more. And we did that at the resolution of 1 cubic meter. And the ecologists, on their side, they adapted their model to this resolution, to 1 square meter in their case, because they work in 2D. So the result is that we managed to bring ecological analysis into Grasshopper and to link it to a 3D geometry. So we can now simulate dynamics between species and their distribution over time in a 3D modeling environment. Well, and as mentioned before, behind these green areas, there is a volumetric data model, a voxel model. And that voxel model displays ecological analysis results such as biomass. Then we have biodiversity, which is the richness of the species per cell. And then we can also simulate the occurrence of one specific species. For instance, on this slide you can see the species Lavandula. And at the moment, our plugin uses a species pool of over 19,000 plants. But not all these 19,000 plants are simulated on one example because it works with local specific data. So the building is, this example is in Madrid, so it only uses the plants that you could find around there. So we can also simulate the occurrence of herbs, such as sedum, and it grows on several soil types that are distributed over the building and the ground. Then also shrubs, such as rosemary, it only grows on a soil type that's placed on terraces on the rooftop. And in this example, this is an example for a tree, the tree acer, and it only grows on the ground as its rooting depth is larger than a meter, and on the terraces you won't have soil that's larger as a meter. Well, and you can see here that the plugin works with different geometry inputs and parametric grasshopper models. So this is one of our earlier test models, and we created these serial plots that illustrate the dynamic changes in plant species distribution, and this over time. And we used in that example, as it was an earlier example, much less species, just for testing purposes. So let's speak data. Behind each color-coded voxel cell, there is a numerical value, and numerical values associated with architecture, the environment, and with ecology. So how do we organize the data in a meaningful way? So the answer is that we use the parametric voxel model. So in the first step, the designer has to define a resolution of this volumetric data model, and all voxel cells are indexed, and each voxel cell knows its neighbor. So it's a kind of graph data structure. Then the data is added as an attribute to each cell, and the index of each voxel cell is directly associated with multiple attributes. And let me briefly talk about the extent of data that we are dealing with. For instance, in our example building, which was just a test case, we have 8,509 voxel cells and 1,755 attributes per cell, because we compute spatial temporal data. So the challenge of mapping a vast amount of data lies in extracting meaningful insights from it. So proper analysis can reveal the correlations between the form of the building envelope and its ecological performance. So simply put, through the data, we can actually find out which architectural design supports biodiversity and which ones negatively impact species richness. So yeah, for this reason, as we had a lot of data points, we had more than 5 million data points, we designed an experiment using a machine learning model. So first, we brought all that data that we generated in our Grasshopper plugin as a training data set into a machine learning model, and we wrote this machine learning model in Python. And on this slide, you can see how the data set of the example building is visualized in Python. And then in the next step, we try to find out which parameters are relevant for the occurrence and growth of one specific species, in this case, lavandula. And we asked the question, what changes need to be made in this example that its form supports the growth of lavandula? So what does need to change in that geometry? So for the machine learning analysis, we tried different algorithms. For instance, the decision tree algorithm from the Skykit-learn package and CatBoost algorithm from Yandex Technologies. And both of them, they returned similar results. So the machine learning decision tree algorithm identified shading and height and soil depth as key factors affecting the growth of lavandula, and also in this order and in this importance, as you can see on this graph. Our findings show that lavandula thrives in areas with minimal shades, height above 4 meters, and soil depth over 15.5 centimeters. So this was actually interesting information. So based on that information, the building form can be optimized. So the optimized building form introduces larger terraces facing south and a structural design that supports more than 50.5 centimeters of soil on the roof and all terraces that are above the height of 4 meters. Well, so a few words about the architecture. Analysis and simulations and our training database, and to put the data in our training database, we have to deal with computationally heavy processes, so that's why we used for all of this Rhino compute on a Windows cloud server. I don't know, anyone has heard about Rhino compute? Okay, so we have some people that know about it. So Rhino compute is basically Rhino Insight running within a HTTP server environment, and so it can be used as a backend service to bring process-intensive algorithms into the cloud, and the system communicates with local machines through a REST API. Well, conclusions. Although the Grasshopper plugin with the ecological model is a very simple start or a simplified start, it still already incorporates the dynamics of plant species, and we have the species pool of more than 19,000 plants, and it connects architecture in some sort of way with biodiversity, and the plugin speaks for the ones in a way that cannot speak, which are the non-human species, and it considers in some sort of way their requirements in the design process. Well, the parametric voxel model, it effectively represents geometry-related attributes at a predefined resolution, and this was the only way to make it compatible with the ecological model. And also, I think GIS models, they work in a similar way, so it could be also compatible with them. And volumetric data models, they can be used as training data sets in AI approaches. So we see this actually also in practice a lot, that people use Grasshopper to generate training data. So it's a kind of synthetic data that's generated by changing some sliders in Grasshopper. So what's next? Yeah, we are working already with landscape architects together, and they really ask us that we need to include existing vegetation, that we start not the simulation from zero, but that you start at a point where you already have something growing somewhere. And we want to extend analysis and simulations to the scale of the neighborhood and consider artificial irrigation systems and extreme climate events. And there is already a model around that is computing the species dynamics between animals and birds, especially birds. And yeah, we try to maybe bring that into the plugin or make it available, and maybe grasshoppers, as you can see here. Well, yeah, upcoming events. Carlos already told you about these 2 events. Well, so thank you for your attention.